Hi, I would like to begin with sharing my first experience with modern C++. So I've been a programmer in C++ for just about 12, maybe 13 years by now. And at some point, I heard about this new standard called C++11 and the new features such as unique pointer, lambdas, or range-based for loop. And I was really, really eager to try those out. But, well, I tried them out, entered some source code, and tried to compile it. And then had to find out, well, my compiler didn't actually support C++11 at the time. And this is a common theme I've heard from lots of people since then. Whenever a new cool C++ feature comes out, with C++14 or 17 or now 20, they can't really use it even though they're really excited about it because the compiler does not support it yet, but maybe just in 2 or 3 years. So that's why I went out of my way and created this tool, which is a source-to-source compiler that allows you to keep using your current toolchain, but translates your source code to an older version of C++ so that it works still. But I'm getting ahead of myself. Let me just really quickly introduce myself. I'm a C++ enthusiast who likes to find a synthesis between systems programming on the one hand and type safety on the other hand, because I see this is a really well, within our community, it's becoming a more prevalent position. But if you think about it, when you're working really close to the hardware or describe hardware registers or things like that, then people generally just resort back to C programming because that's the most direct way to describe these kind of systems. But type safety really doesn't affect performance if done right, and still gives us a lot of safety guarantees and invariants and allows us to statically verify properties of our program at compile time. So why not use it more often? I've been using that, applying these kind of techniques in game console emulation, most importantly. So if you've ever heard about any of these projects by any chance, those are projects I contributed to. Most importantly, probably the Dolphin emulator, which is the Nintendo GameCube and Wii emulator project, where I worked on graphics emulation. And again, these kind of type safety guarantees really, really saved me a lot of debugging time a couple of times. Right, professionally, I'm doing consulting. If you ever need advice and help on code modernization or code reviews or need to help me find better ways to get your job done more efficiently, that's things I can help with. And yeah, I think C++14 and 17, well, my personal mission, first of all, is really helping people and establishing better ways of writing type-safe and correct programs. And I think C++14 and 17 are key pieces of technology that help us getting there, even if it's still not ideal. So why is that? Let me give you a couple of examples of how C++14 and 17 help us write better code. I've vaguely identified 4 categories here. The first one is kind of the syntactic quarter, which is things like structured bindings, which really started to make multiple return values from a function feasible, because now instead of returning a tuple from a function and individually destructuring it using std_get, we can just destructure it automatically into different variables. Also, binary literals and digit separators make it really, really much more easily and readable to have constants in your code. And one typical example in my work was bit masks. When I'm interfacing with hardware registers, for instance, you often want to set bit 1 and bit 7 of a particular value to 1, or I want to mask them off, whatever. And then you end up with these magic constants such as 130, for instance, and nobody really understands where does that one come from. So C++14 added the capability of writing that down as a sequence of zeros and ones instead. So the way the magic constant is calculated in the first place becomes much more apparent. And there's also the digit separator, which is the apostrophe you can see right here, which allows us to visually group groups of digits, so you can easily tell that this bit, for instance, is at position, well, at the most significant bit, rather than at position 6 or 7 or whatever, where it's always somewhat unclear. And it might not be a particularly type safety feature, but it helps us write more correct code because it makes code review much easier. If you can easily verify this constant is the correct one rather than that it's missing a 0 somewhere, that really helps. Another example is the merged declaration and testing syntax for if statements, where instead of declaring a variable outside the if statement and then testing for its validity, we can now do so in one go, while limiting the scope of the declared variable to the if body, which can come in handy at times, especially when working with third-party libraries like Qt, where qvariant is not like a null pointer that can be checked for null, but you have to call isValid on it. Right, so that's the kind of syntactic extensions we got. There's also standard library additions such as std_optional and std_variant, so std_optional in particular allows us to have a unified interface for handling scenarios where a function might not return a function value, which you might use as a replacement for error codes, for instance, or status codes more importantly. And variant is a nice type-safe union where it's always clear which of the union members is active. And then there's other syntactic extensions which help metaprogramming and which provide us a kind of code generation facilities, such as fold expressions, for instance, where using fold expressions you can very concisely write down complicated expressions that work on variadic templates. So if you just want to have a parameter list of bars and then want to call a function foo on them and sum up all the results of these function calls, you can do so really, really concisely using this fold over a plus operator. Similarly, we got ifconst_expr, which allows us to do static branches at compile time, such that you can conditionally enable code depending on properties of the input types, which is a very huge simplification compared to C++11, where you might have needed to resort back to sphenatrix, for instance. So overall, these make writing code much more easier and much more accessible to beginners as well, because the code, even if you don't understand it, it looks rather intuitive, because you can probably guess that total foos is summing together all of these function calls. And then in the fourth quarter, we got functionality extensions such as the std_filesystem library, which I won't be talking about too much today, but it's worth mentioning that we now have a standardized interface for file system access. Right, but there is a problem. There is a problem, maybe not for everybody, but if you look at this code sample, getMask, which is just returning the binary literal with digit separators we've seen before. Maybe that's just a way of encapsulating this constant, I don't know, but anyway, we got this in our code base and we want to compile it. Well, send it through GCC 4.9 and you get a binary output out of that, just a x86 assembly that moves the value 128 into the register and then returns. Gives us a happy face programmer. Try the same with GCC 4.8 though, and you will get a very angry, or at least an annoyed programmer, because, well, GCC 4.8 does not support digit separators. That's really frustrating because, sure, the feature wasn't particularly important, but it certainly helped make the code more readable. So it's kind of annoying if you have to refrain from using a particular feature that helps you to write more readable code just because a compiler doesn't support it. Especially when, in this case, there's not really any particular reason the compiler doesn't support it. It's really just a syntactical, like a front-end thing. So why can't we patch in the support in retrospect? So what can we do about this problem? Well, first of all, upgrade your compiler. Just don't use GCC 4.8. That's an option for you. It's not always an option. Sometimes you're working on platforms that just don't have any more up-to-date compiler. Maybe GCC 4.8 is the most up-to-date toolchain version your vendor provides you with. This is particularly an issue for embedded systems, for instance, where maybe the board that you're developing on is even obsolete by the point you're developing the software, so there just won't ever be an update to the compiler. Maybe updating your compiler is just too invasive. You have a huge pile, like a hugely over-designed build system that relies on this particular compiler version, and upgrading it would just be too costly for it to be worth it in the short term. What can you do instead? You can stick with older C++ and put up with the consequences, of course, which might not be too bad depending on your view of it, right? We've been using C++ 98 and 03 for quite a while, and they did get the job done. But ultimately, they're outdated technologies by now. There's better tools to do our job these days, precisely in C++ 17, so why not use them when they are available? So up until now, these were pretty much the only two options that we have. So that's why I started to investigate what we can do about it. And my idea was to allow people to keep using their current compiler, but allow them to teach that compiler how C++MT works. And that's where my software clang-from-the-future is coming in. Small disclaimer in the beginning, this used to start out as an open source project. It's now actually a closed source, like licensable model for reasons I'll get into later. But yeah, let's look into how that actually works in practice. So it's designed as a libclang-based preprocessor for your compiler. So what that actually looks like is you have your regular source code, feed it into your normal C++ compiler, then into the linker, and then you get the executable out. But with clang-from-the-future, you insert these kind of two additional build steps, where first of all, the tool will parse the source code and build a tree-based representation. And then we'll do some fancy pattern matching logic to identify C++14 and C++11 nisms, and then transform them to their equivalent C++11 source code. And then that intermediate representation is fed into your actual compiler, which then will be able to regularly process it and generate an executable from it. So yeah, this entire design allows us to fully automatically convert the source code on the fly. You just don't really need to do any kind of changes to your tool chain, but it just works. Right, so we get this additional enhanced pipeline. And one example is, if you look at this getMask function, the tool will modify this to, instead of using the binary literal with the digit separators, just hardcode in the actual constant. And this is great because as a developer, we can now work on the left side of the slide, where we can use all the cool new features. But on the right side, that is the C++11 output, which the compiler actually understands. So we can use the new syntax even though the compiler does not support it. Right. So looking back at our angry face programmer, we can now chain CTFT in the beginning, feed that into GCC 4.8, and again, we get a happy face programmer out of it. Right, so how does it work? First of all, before I get into that, I wanted to mention, if you've got any questions at any time, feel free to raise them in the beginning. If you raise them immediately, I don't mind. But yeah, how does it work? So as I've been mentioning, it's a libclang-based tool. You might have heard of it, and there's actually quite a couple of tools based on that. So I just vaguely looked up a couple of them, just to see here. So the most well-known ones are probably clang-format and clang-tidy. There's also a tool called CppOnSea, which is quite interesting, actually. It provides an automatic generation of C wrappers around C++ APIs. So if you ever wanted to interface with Python, for instance, you could use that to exchange data between a Python front-end and a C++ back-end, for instance. There's also C++ Insights by Andreas Fertig, who's actually sitting right here in the room, and who actually also talked about this at this conference yesterday, I believe. So if you want to learn more about that, check it out. But basically, in a nutshell, it's an educational tool that is used to show people how modern C++ features work under the hood, such as a range-based for loop, which is really nothing else but an iterator-based loop. And then there's a couple of reflection frameworks. Arvid Gerstmann has actually been talking about that, is talking about that at this conference. So if I'm boring you right now, I believe he's speaking in the main hall, and you can go over there. And yeah, there's a couple of static analysis and tons of custom tools that companies are using internally to verify that their code is working as expected, to catch bugs that come at analysis time, and other things. And yeah, clang-from-the-future is basically one of these tools that is now, it's one of these tools. Anyway, what libclang provides us with is an abstract syntax tree representation of the program. So if you've never seen one of these, let's look at an example again on the getMask function. And what libclang will provide us with is this kind of tree representation, where the top level node will be the function called getMask, which we get as a function declaration object, which has 3 children in total, one being the return type, one being the parameter list, which in this case is just empty, And then on the very right side, we got the return statement. So the function body, which in this case is just the single return statement, which in turn also has a single child element, which is the integer literal. So what we could now do using this tree representation is we could manually traverse that tree and see, okay, if we got an integer literal, replace it with the actual constant. But libclang even provides us with a nice interface for this, which is called an AST visitor, which is basically the idea is that you call a C++ function for each particular node type. So looking at the graph we see before, we now have for each of the nodes here a function such as visit function decl, which is called whenever we encounter a function declaration. And we got a visit palmbar decl function that is called for each parameter, and so on for the others, and so on for the integer literals. And by the way, what I forgot to mention on the previous slide, you can easily dump this AST representation using the command shown at the very bottom of the slide. So that's quite interesting to look at sometimes, especially because it's nicely colored and you can easily see the structure of your program that way. But yeah, let's look at an example of how this might work in our particular case. So we just have a function called okay, interesting. So we have a function called a visit integer literal, which is a member of the class myAstVisitor, which is derived from Clang's recursive AstVisitor class. And what we do in here, we get the integer literal as a parameter, and then first of all, we want to get the value of this literal. And we just do that using a function called getValue. It's really, really simple, as simple as you might imagine anyway. And then we've got a rewriter object, which basically takes care of all the source transformations, and tell it to replace the, what Clang calls source range. So basically, the source locations that correspond to the string in the source code. We replace that with the decimal version of the value we just decoded from the object. So the implementation of this visit integer literal, that's part of clang-from-the-future, but all of the interfaces you see here are part of Clang, other than the actual rewriter functionality. So libclang has a class for rewriting source code, but it's rather limited in a sense. So it's really designed for one-time replacements of simple strings with other strings, whereas clang-from-the-future, as you might expect, needs to do some sort of nested replacement sometimes. So imagine this kind of literal occurred inside of a fold expression, for instance. So the fold expression, of course, will need to be instantiated multiple times, but then within the instantiated expression, you will also need to replace the integer literal. So you get basically multiple replacements on top of each other. And libclang does not support that, so I had to reinvent the wheel here. Right, if we do this and try it out, that's really pretty much all that you need. There's some boilerplate code to get the tool running in the first place, but with this simple function, we get the replacement already, so I find that quite neat. And when I tried that out, basically that was the first thing I attempted to do a prototype with. Then I was like, okay, this was really, really easy. Let's try out something interesting. Let's try out const expr. And to say the least, that was somewhat naive, maybe. But well, let's see what kind of issues I've encountered. But yeah, let's be optimistic and assume it just works. So let's look at an example, a function called makeSound that takes a template parameter, which could be either a cat or a dog. We want to make that animal do their respective sounds. So for cats, we want it to meow, and for dogs, we want to make it woof. So the way we can do this is with an if const expr, so a static branch, and we detect whether the type is a cat, we're using std_is_same, and if it is, we make it meow, and otherwise we assume it's a dog and make it woof instead. And Clang has no problems at all parsing this. We get an AST out of this, where our function declaration does not have a return type, but it does have a parameter list. and its body is an if statement, which in turn gets the condition, the if body, which is the meow, and the else body, which is the woof. Now, in reality, it's a little bit more complicated for those call expressions at the bottom, but for the purpose of demonstration, that's all that really matters. And what we basically want to do is we want to hook into this if statement using a custom visit if statement function, and then do some sort of replacements. But here comes the problem. Which branch is actually taken? See, the issue is we got only one definition of the template in the source code. So if we want to statically decide this, we need to decide which branch is taken, but there's just no right choice here. So I've been thinking about how to address this problem because, well, I needed to come up with something, and thought about what is the compiler actually doing internally. Well, what the compiler is doing, it will create two different copies of that function template, one specialized for cats and one specialized for dogs. So you get these implicit specializations of the function template. And when you do that, it's really easy to decide which branch is taken because you know all the types in your program, so you can't statically evaluate this condition. So what I decided to do is, well, maybe I'll just make what's implicit for other compilers explicit. So I'm generating two different versions of this template. First of all, for cats, calling make sound. And what I do is, since I'm now in this specialization that the template parameter is a cat, I can evaluate this condition, keep this meow, but I can cross out the woof. So the code will still compile now because now the cat isn't being called with a woof instead. And on the other hand, if I got a dog, I'm crossing out the other branch and keep all the other bits around. So it might seem a little bit odd that I'm keeping around the condition. That's mostly done for the sake of side effects maybe, or for instance when declaring a variable in the if statement. So it's basically the principle of modifying as little of the input source code as possible so I don't run into the danger of introducing any bugs. And yeah, in particular, I'm not rewriting this T. Instead, I'm actually re-exporting the template parameter in the function definition, which is like a little neat trick that I do so I don't need to go through the entire function body and do possibly invasive replacements. Yeah. Question right here?
You don't really know that so looking at the top, you have no idea that dog is the only other possibility for the thing.
Right.
Right? So wouldn't this just be like, wouldn't the definition on the right be the same as the one on top, where you just added the specialization to the cat type?
So let me just repeat the question so I make sure I understood it correctly. I believe it was that I don't actually know the types that are being passed to this template in advance. So I don't really know which types to specialize the template function for. Is that it?
The definition on top has the cat type in it.
Mm-hmm.
You can see how you can parse the tree and then form
Right.
the implementation on the left. But you wouldn't be able to form one on the right unless you're saying somewhere else in the code somebody called the function with the dog type.
Right.
Is that what
Right. So the comment was that for cats, it's easy to see why I need to instantiate this function because it already occurs in the template definition. But it's not clear why I'm coming up with a dog here. So libclang actually provides us with a list of implicit specializations that it would have created. And that's based on the function, the way the function is used later throughout the current translation unit. So if somebody calls make sound only with cats, then clang-from-the-future wouldn't be generating the dog specialization because there's no need to. Right. So in summary, what CTFT is doing here is it turns the implicit instantiations of the template into explicit ones so that the front-end compiler doesn't need to worry about that. And it might not seem like a big deal, but you can see based on these little oddities, such as re-exporting the template parameter, that this is actually quite the involved task. And as a matter of fact, currently this makes up just about 50% of clang-from-the-future's code base, ignoring tests. So it's really, really involved. Right, but if we got this kind of engine, we can now write this visit if statement function, which in this case I would only run for each implicit instantiation separately. So it's called once for cats and once for dogs. In the beginning, I can just check, is the current if statement a const_expr statement? If not, there's nothing for me to do because there's no branches I need to statically remove. However, if it is, I keep going, and the first thing I want to do is check what the condition is, and I want to get the result for the current parameter. Let's walk through this. What I basically do is I retrieve the AST node for the condition. So that's the first child that our if statement had. And there's a couple of operations I can do on this condition. And one of these is evaluate as Boolean condition. And that allows us to do just that. It allows us to ask libclang, what is the static result of evaluating this condition? Oops. It needs a context object, which is like a global object in my program, but it's not really hard to get by. And it stores the result in this Boolean variable. And then I just try to retrieve the body statement of the taken branch based on that result. So either I'm taking the if body using getThen, or the else branch using getElse. And once I got that, what I basically want to do is some boilerplate code to actually remove the proper portions from my code. So first of all, I want to remove the const_expr keyword because it's not relevant anymore now. And then I want to remove the inactive branch body. So again, the idea is to not replace the entire if statement with the branch taken, but just to do the minimally invasive thing of crossing out the code that is not relevant. So in this case, it's just, you can look at this offline, it doesn't really matter, but basically I take, well, yeah, in this case, for instance, I'm removing anything, oh man, I'm not actually understanding my own code. But yeah, basically the source locations here are so chosen precisely such that it will remove the bodies of the ifs or the else body respectively. So yeah, and I can confirm that it works in practice, and we will actually later see an example of how it does that. Right, in practice, how do you actually use the tool? Well, as I've been saying, the idea is to automatically to do this fully automatically, but you can invoke the tool manually as well. So it's just an executable called CTFT, which you pass a front-end compiler, just like your regular G++, for instance, and then you give it the input source file. So just as you might expect, the key here is just that it needs this kind of front-end compiler, because otherwise there's no way to tell where to pass the intermediate source code to. But there's also integration into existing build systems. For instance, with make, it's as simple as just overwriting your C++ compiler with CTFT and then adding some additional CXX flags which tell it which front-end compiler to invoke. And you do need to call that kind of command line each time you compile a program. But if you're using CMake, it's actually really, really easy, because you just need to do that once at, is it called generation time, I believe? Where again, you just set up the CXX flags accordingly and export your compiler correctly. But then after that, you just call make, Ninja, whatever build system that you're using, and then it would just automatically pick up the right compiler flags for you. So that's really, really nice, and again, I will show an example of this later. But yeah, other setups may need some creativity. If you're using Visual Studio or Xcode, there's no out-of-the-box solution for that yet, but eventually. Right, so showcase, I wanted to give a couple of examples for how this tool works in practice and what kind of transformations it's doing. So let's look at it. I prepared my consoles for this. Right. So first of all, I wanted to show off the actual, did I got the right one? Yeah. The make sound example from before, where I just provided some really, really simple dummy implementations for a cat that meows and then doesn't actually do anything. But yeah, it's nothing really different from the slide we've seen. So let's see what the compiler, what CTFT is doing with that. So I can just say CTFT. Is that big enough for the last rows, by the way? It is, lovely. So just say front-end compiler, and in this example, let me just use G++. And say 1a const_expr and tell it which compile, which C++ standard to compile against, and it will just work. So the idea here is, right, the idea here is that all of these compiler flags can just be passed to CFTF. So these would be like the G++ syntax, and you could also add things such as -w all here, and it will just be passed through directly to your front-end compiler, unless it's the C++ standard, in which case it's intended to downgrade the version accordingly. I'm not sure my current build is doing that, but that's basically the idea of what will happen. Right, and as you can see, it's invoking the front-end compiler using a temporary file here. So let's look at what the actual output looks like. Right, and you can see it's a little bit different from the left side, but basically the definitions at the top haven't really been changed. The template function make sound that we had originally, that one's now just a forward declaration. So the compiler knows, okay, this thing exists. And instead we now have an explicit specialization for the structure dog, where we replace this generic template parameter with the concrete type dog t. And then we just basically see the same content on the slides. And you can probably tell the formatting isn't really nice here, but that's pretty much because it's out of the scope for the tool, because it's just intended as an intermediate representation that is then fed to the compiler. So generally, you won't need to look at this in the first place. But yeah, we could run clang format over this and it would be a little bit more readable, but you can see here for dogs, the if statement now contains an empty branch body because it wasn't relevant, because we're talking about dogs and dogs can handle only wolf. And yeah, that kind of connects to the question we had earlier about what actually happens. Like, how does the compiler know which types to instantiate the function for? In this case, I commented out the make sound for cat call, so the translation unit only ever calls the function for dogs. So it only really needs to specialize this function for dogs. But you can just see what happens if we don't do that. And instead, we enable this, compile it again, and check it again. That's interesting. So this is supposed to work, but apparently it doesn't. So I've been doing some last-minute changes, and apparently that broke this particular example. But in general, you would have seen like a second implicit or explicit instantiation generated, just like you've seen in the slides before. Amazing, yeah. So the remark from the audience was that my command line was just wrong. And apparently I need to work on my command line parsing library. Oh well. But yeah, at least the example now works fine. As you can see, we now have the first instantiation for cats and the second one for dogs, just as expected. Right. So the idea is to just go through a couple of more examples now. The second one has slightly more interesting definitions of the meow and woof examples. So in particular, the difference here is that cats now return an integer after meowing, and dogs return a string after woofing, which is a very natural interface to design. And the idea is that our make sound function will now return the respective return value from woofing or meowing. We can use C++'s auto return type deduction feature for that. Because if we have a cat, it will meow, it will return an integer, and then our make sound function should return an int. If it's a dog, it will return a string though. So the compiler should automatically pick the right return type for us. If you think about what I've shown before, that's kind of non-trivial because we had this function template forward declaration at the top. And we need to have a well-defined return type at that point for things to work. But I came up with an interesting trick to make that work. So let's see what CTFT produces with that. Right. And because we will always be doing this kind of thing, like compiling the sample code and looking at the intermediate representation, I wrote a small utility front-end compiler called edit.sh, which runs clang format on the intermediate representation and then opens it in an editor. So that's not really a compiler, but it fits the interface, so you can see it works. And what clang-from-the-future is inserting here is there's utility type, this utility type called CFTF deduced return type for make sound. And the idea is this is a template type that gets all of the template parameters for the original template function, and then uses this helper type to forward declare this make sound function. And the advantage is that we can capture all of the different return types like this without any particular issue. And yeah, there's a lot of boilerplate here to actually define this, but at the end of the day, we also get our implicit instantiation with a respective return type for that particular parameter combination. So that's quite fun. And yeah, this kind of stuff can get really, really ugly if you use that string, for instance, because it uses the fully expanded template. But oh well, it works. Right. Yeah, sure.
Is the source code on the left, that valid C++17? I mean, with context for if we can let the compiler use the return type?
Yeah. So just say G++. I got a fairly recent version of that on my system, so that compiles G++17 just fine, and it works. So the question was whether the code example was actually a valid C++17 code snippet, but yeah, it is. Let's see the next one, structured bindings. We have a function called myFancyFunction that returns a tuple with different kind of types as a return value. We can now use these structured bindings to destructure that into a string variable and a number, and then print those out separately, which is, in my opinion, rather more readable than using stdcat anyway. So if we compile that, what am I doing? If we can compile that, right. So first of all, it also deduces the auto return type here, because that's again a C++14 feature with the actual tuple type. But more importantly, at the bottom, it stores the tuple return that in a temporary variable and automatically generates these bindings by calling stdcat on them individually. So that's just a very blown up version of what you would what your mental model of structured bindings probably is. And it just stores that into variables and then just works. Right. And this stuff works for other applications of structured bindings as well. So you can have a user-defined structure, which you can also destructure using this approach. Again, there's not really much to that. And you can just see, again, it will create separate variables that just extract the proper proper data member of that structure. So yeah. Let's see, what else do I have? It's another structured binding example, but this one isn't too exciting really. Not actually sure what's different from the previous one, but well. Let's see what else do we have. 0-3 structured bindings. Right, and again, you can have the same thing for structured bindings with user-defined ways of destructuring the thing. I won't show you what clang-from-the-future is doing with that, because really it's just the same thing over and over again. It's just worth noting that all of these edge cases, like different ways of using structured bindings. All of them are supported because all of them might be used in their code. But yeah, let's get to something more interesting, which is fault expressions. And I actually had a very important applications for this in a personal project, and that is the ESP32 development board, which is a rather popular microcontroller for for Internet of Things applications. And they released a fairly up-to-date C++ compiler. It actually goes up to C++14, which is rather nice. It's easy to work with, got lots of interesting features, but they haven't quite made the update to C++17 yet. And there's another conference talk that I've given about how you can use C++17's fault expressions to automatically generate things like communication protocols and serialization and deserialization problems. I really wanted to apply these techniques in this context, but couldn't. So I basically tried out the tool that I wrote with this compiler, and it works, as I can show you in a minute. But yeah, say we have a function called sum, quite similar to the one I showed in the beginning, which just takes a couple of integers and sums them together. Or well, general objects that have a plus operator, but yeah. And we can call a couple of statics assert with that, and all of them technically should compile. So let's see what happens with those. Right. And what clang-from-the-future is doing here, again, it will turn these implicit instantiation of the variable template into explicit ones. So for each of these statics asserts, one of the versions on the right will be generated. So first of all, we got a single parameter version, which just takes a single parameter instead of a parameter pack this time. And it expands that fault expression into just TS plus 1. So that's simple. The one for 5 parameters will replicate this parameter pack into multiple explicit parameters and actually number them so that each parameter gets a unique name. And then it will just replace the sum with TS1 plus TS2, etc. plus 0. And then we get the empty case at the very bottom where we just remove all the parameters and the usages in the body. And then at the very bottom you can see the static asserts are untouched. So if this transformation was correct, our program should still compile with a proper compiler. So let's see if it does, and hopefully it will. So for that I will change my compiler to this one, which is the compiler I would use to target the ESP32. I can quickly show you actually. That's a GCC 5.2 version, so it only supports up to C++14, unfortunately. But yeah, if I use that as a front-end compiler and skip linking because I didn't define any main, you can see it invokes this kind of compiler at the very bottom and then outputs nothing. So that means our translation unit was compiled successfully without any errors in the static asserts. So our transformation apparently was correct. So that's quite nice. And it's interesting to mention that this kind of approach isn't limited to C++17 to 11 transformations. Because as you've seen, there was nothing C++11 specific in the code on the left before, other than the static asserts, of course. The fault expressions were actually translated back to C++03 in a sense. So you can actually apply this to plain parameter packs as well. You just have a plain and simple parameter pack with like a couple of if-const express in there. You can again run this through CFTF and see it will again instantiate the thing. In this case, it's a recursive function, so it will cascade from 5 parameters to 4 parameters, etc. But at the very top and bottom, it will again just have the static asserts, which should just pass. So there's that. Right. And I think, yeah. So that's pretty much the end of the practical part. There's just one more thing that I meant to show off, and that is the build system integration, which is maybe somewhat interesting. So there's the test case of the tool itself, which is basically just a bunch of C++ programs. Let's just create a new build folder in there. And now I'm using the command line I've shown before, right here, to set up the build system. And call it on the parent directory. Yeah, that's not going to work. Should probably be in the actual test directory. You can see it will do the typical CMake tests, and in particular it will check for a working CXX compiler. It will identify that our CFTF binary is a valid and working C++ compiler. Now we can just call make. We'll run through a couple of things. And presumably this is where my last minute changes come in. But basically you can see at the very top that it will do a couple of will attempt to compile a couple of C++ files automatically and then just go through it. It's a shame that it didn't actually work in this case, but yeah, that's just how live presentations and live demos work sometimes. But yeah, in theory, if everything had gone right, this would have just cleanly run through and you wouldn't really have noticed any of it. But well. Good. So with that said, what are some potential use cases that I have in mind for this? So again, just using C++ in 17 is worth it in my opinion. But yeah, basically if you want to early adopt new standards, such as the coming C++ 20 features, CFTF might be a valid route of doing so. Currently it doesn't support C++ 20, but in the future it might. So if you want to use C++ 17 libraries, such as range v3, and in C++ 11 setups, you could run CFTF just for those specific libraries. If you want to port an existing piece of software that already works, but maybe it was developed against a modern embedded system and you want to retarget it to a different system that doesn't have such an up-to-date compiler anymore, that's a valid application as well. Or maybe you just want to cherry pick very specific features such as concepts or contracts, which easily can be supported using this kind of approach. And you don't care about any of the other backporting features, but really just about being able to use those specific features. So again, that might be a valid application. Current status, it's working. It's working on GCC, for GCC and Clang as front-end compilers, on Linux and presumably on macOS as well. Proper support for those platforms, including Xcode and Visual Studio integration, is certainly on the roadmap, but not quite there yet. And yeah, the initial set of features that are being supported is still rather limited. Largely, you've actually seen most of them in this presentation, simply because I'm trying to make this rock stable so that we can be sure that the transformations do not introduce any bugs, because supporting C++ 17 is useless if you cannot be confident that the transformations will actually produce the same result. Right, so the idea is that I want to be open to licensing right away though, so that you can influence the development and tailor the software to your needs, depending on what specifically you want. There is a prototype available on GitHub. It's a rather old version by now, but if you're interested in how specifically CFTF works, and maybe want to see a couple of tricks that it uses, you can still read that code, and I'll probably be keeping it up for, well, I don't plan on taking it down is what I'm trying to say. But yeah, if you want the full power that is currently implemented, you will need a license for the whole thing. So yeah, the future. First of all, I want to And I'm actually quite surprised nobody asked a question about this. I want to provide a better debugging experience. And that's actually a quite major drawback of the approach right now. Because if you take the C++17 source code and rewrite it, and then compile it using the front-end compiler, well, the front-end compiler will create debugging symbols and source locations respective to the intermediate representation and not to the actual source code that you wrote. So I've got some ideas on how to address this. Basically, the idea is to patch up the debugging symbols in the ELF binary or whatever system you're working on with the appropriate source locations. That's a rather ambitious project, but I think it can be done. It's just something I haven't really gotten to yet, but it's pretty much high up on the priority list. After that's done, I really want to have more test cases. I want more test coverage in the first place for the language features, and I want to throw the tool on actual C++ applications in the wild. So let's see how well that works. And the next step might be to not go from C++17 to C++11, but further beyond. I've heard the sentiment a lot that people are kind of like, meh, okay, seems nice, but But then if I mentioned, hey, you could port this, you could extend this to also translate C++11 features back to older versions, all of a sudden they got really, really excited about that. So maybe there's a bigger market out there for that. And yeah, we'll see. Could go the other direction, contracts and concepts, as I've been mentioning before, features that basically are only syntax and which can largely be supported by this approach as well. Robustness against macros. So if you use macros on your code, that won't break clang-from-the-future right now. We can do some rather nasty things, such as compiler-specific branching within a macro, and then doing some things that are not self-contained, but that kind of generate IST nodes on the fly. So if you're doing nasty things, that might break the transformation process right now. So I'm trying to be more robust against that. And finally, I want to extend platform integration because I realize make files and CMake are not what everybody is using. And Visual Studio and Xcode are certainly high up on the priority list there as well. But yeah, ultimately, I'm curious, what are your wishes about the tool? What do you think I should be focusing on? Let's have a conversation if you like. So yeah, to sum up, clang-from-the-future is a libclang-based tool that allows you to compile C++17 and 14 on old compilers that only go up to C++11. The idea is to have a functional drop-in preprocessor that just cleanly integrates into your build pipeline, so you don't need to worry about it, while still being able to easily integrate it to your existing build setup. And finally, the idea is no source code changes. Ideally, you will just write your C++17 source code without noticing the tool at all. Yeah, if you want to see more, again, the prototype is in GitHub. This is me on social media, and if you have any questions, you can send me an email. And I believe we still have a couple of questions, so anything? Yes, please?
You're mentioning about debugging being a problem.
Mm-hmm.
If I go one step simpler and I have compiler errors, firstly, I didn't some C++ thing to say where a line of source comes from. I didn't see that in your code.
Right.
If I have a compiler error, will the warning point to the right place?
Well, let's just try it out, I suppose. What happens if I remove the semicolon here? Well, no, I'm in the wrong directory for this one. And this is which file again? This one. So I won't even be bothering setting up a front-end compiler here because I don't need to. What CFTF will be doing under the hood is basically it invokes Clang just through this library libclang. And libclang will actually output all of its regular error messages if anything is wrong, respective to the input source file. So you'll see in the input file at line 4, you get the regular error message with this nice error indicator as well, and it's just fine in that case.
If the error was in my use of the new feature, don't quite know what I have in mind, so I can help you.
So basically, if anything is wrong with your, so the question is all about what if the input source code is not valid C++? What if there's a compile error and how do I find it? But in principle, if there's an error in your code, be it in C++11 source code or in the newer features, it will be called by CFTF at the clang compilation level. So if there's any error in your code, it won't ever pass on to the front-end compiler in the first place. Yeah, because it will all be caught in the first layer of translation, basically, and you get to see the original input header lines.
So one common thing with compilers is to try and compile your own.
Sorry, what's that?
One common thing with compilers is to try and compile like your own like source code with it. So I guess CTF is C++17. Like you wrote the CTF in C++17.
Oh, right, yeah, I did.
Yeah, so have you tried to run CTF on CTF?
It's very high on the priority list. I certainly tried to develop CFTF in a way that it can indeed transpile itself, because the idea is, well, if you're trying to target a system that, or if you're in a big corporate institution that cannot afford updating their compiler, well, you cannot compile C++17 source code. So you wouldn't be able to compile CFTF, so that's a hard blocker. So the idea is certainly that CFTF could transpile itself to C++11 in that case. So I avoid features for which this transpilation process would not work otherwise. Right, so if there is no other questions, thank you for having me and enjoy the rest of the conference.